Okay, guys, well, I think we may get lucky and have time to do a little bit with recursion. So let's just do a quick review of recursion, because what I really, my end goal in this is I want to show you how you can call not only one assembly language function from another, but also make a recursive call, the initial call from C++, to an assembly language function definition that then recursively calls itself. So since that's what we're going to do, we're going to take a look at an example. But before we do that, before we do anything, let's go ahead and review. So a recursive call is a function that calls itself. So remember, when you make a function call, you've got the things that are part of the function call, especially pushing parameters on the stack or passing parameters through registers, however you do it, making sure that the return address is pushed on the stack, and then copying the address of the subroutine into EIP. So we know that happens. When that happens, when we copy the address of the subroutine into EIP, it then carries out another instance of execution of its own code. So that's essentially what we're looking at with recursion. So you remember that for a recursive case to work, you actually have to have two cases. You've got to have a recursive case, and that's where you make the call to yourself, and then you've got to have a base case, the stopping case. So both of these two. If you don't have the base case, you're in big trouble. You get something that runs forever or until you run out of random access memory, which probably happens sooner than you think. So your first introduction to recursion may have happened, the stereotypical examples are factorial, towers of Hanoi, things like that. So you saw an example that was iterative, and here we're passing in, and then we're going to return product as a reference parameter. And here's the iteration where we go through and calculate it. But we can also solve this recursively in C++, where again I pass, in this case, just n, and I have the two instances. Here I have the recursive case, where I see as part of this return statement is actually going to have to execute this expression before it can return the value. But part of this expression is this call. This call is going to have to return a value before the rest of this expression can be calculated. So that's the recursive case, and over here we see the base case. So I've got both, and this actually is the one that we're going to step through. So you see here, it looks really nice. Recursion in high-level languages, it is deceptive because the code looks straightforward. And I say it looks straightforward, but we know what really happens when we have that many calls to a subroutine. The way we write recursion code, it also hides the underlying stack manipulation and produces code that, frankly, is a little more difficult to trace. So there are some downsides to it, however, you will see it. So let's look at what we would do. All right, in C++, again, this is more, more of a review. When you first learned about recursion, you were introduced to activation records. So an activation record is let me just tell you this is the same thing as the stack frame or the entry code. What do you do to get ready before you ever execute a function? So it contains information as to where the function should return. Oh, that sounds like a return address. And then it also contains values of the local value or local variables and parameters. So yes, looks like all of this is what we would do as part of establishing a stack. All right, so let's look at factorial. Let's suppose we're going to execute that piece of code. And what we want to do is just kind of trace through it first, kind of easily, and then in class we'll draw some stack pictures of this. Okay, so first call to factorial. This comes from the main function. Okay, so this comes from C++. I pass the value 4 to the function here, and 4 is greater than 1. So I'm going to execute this return statement, but again, I've got to calculate or evaluate this expression, which means I'm going to have another call to factorial, this time sending 3 n minus 1. So the second call to factorial is going to come from within that assembly language code itself. So in the next call, I'm going to be passing, in this case, 3 to the function. And again, 3 is greater than 1. So I'm going to execute this again, calling the function again, passing this time 2, and so on. 2 is still greater than 1. So we execute this one more time, this time passing n minus 1. Okay, with n minus 1, we finally, this fails, and we finally get to execute the base case. So this is going to return 1. So remember, what's going to happen here is return 1 is going to return the value 1 to the previous call. So it's going to return that value 1 and then try to finish the evaluation of the expression n times that return value. So when we go back, we return 1, we multiply it by the value of n at that previous instance, which was a 2, so we return 2 times 1. So we're returning this value, though, again, to the previous call here, where n was 3, so we're going to execute 3 times 2 in this next instance. And then finally, we return 6 to the instance before, and here we execute, finally, the return value of 6 times our current value of n, and we get a final value of 24, which is what we would expect from this in the first place. All right, so let's try to kind of work our way around this, figure out what we would do. So Fibonacci sequence. You guys probably, I'm hoping you've seen it before. The Fibonacci sequence of numbers is a sequence of numbers that starts like this. Fibonacci 1, 1, 2, 3, 5, 8, 13, ... where, as you can see, the current number is the sum of the previous 2. So if I were to define this recursively, we would get, for the base case, or n equals 0 or 1, f at n, equals 1. Okay? And then for the recursive case, where n is greater than 1, we would say f of n equals f at n minus 1 plus f at n minus 2. So, if I were to look at this in code, I would see it a couple of different ways. Here it is as a value returning function, where in this case I pass in n. Okay, if n is greater than 1 or less than or equal to 1, return 1, else return this expression, or the result of this expression? Well, in order to evaluate this expression, I'm going to have this call to the function and that call. Before I can do it, I have to have both of those calls done. So that's what it looks like. Value returning, you can also write this as a void function. So how do we call a function recursively from C++ to assembly language, or from assembly language to assembly language? Because what we're going to do in class is I'm going to show you how to write one function definition that works regardless of who calls it, as long as the calling convention is the same between all parties. So that's what we're going to look at. But before that, let's just go back real quick and remember some of the things that we had to do. So in our calling convention for C++, the one that we've been using, C++ pushes the function prolog on the stack, so we'll ignore that like we have been doing. And then it pushes the parameters in reverse order. So what I want to do here, we're calling a procedure that adds two values together, passing the two values as parameters. So we're passing value 1 and value 2. But what I want to do actually is execute it this way. So I'm going to pass value 1 as a reference parameter. That way I can store the results in value 1. Well, to do that, if I'm passing those two, the call, it's going to have a parameter list that says v1, v2. I'm going to push v2 first. v2 is getting pushed by value, so let's say v2 happens to be in EAX. Okay? And that gets the value of v2 on the stack. And then I need to pass v1 as a reference parameter. So I'm going to have to load the effective address into EBX of v1 and then push EBX. After that, I'm going to issue the call to, whatever we're calling it, add 2, and then this will do, this is step 2 of our calling convention, that's step 3. Step 4 says after we've executed the code, C++ will clean up its own, what it pushed on the stack, and what it pushed on the stack was our 2 parameters. So we'll just write that in here. We've looked at all of this, or code similar to this, in disassembly when we've looked at another piece of, whoa, that's not going to work. When we've looked at another piece of code. But just a reminder, that's doing exactly what we would be doing if we were doing this in C++. So we are mimicking the C++ calling convention, declare spec, in assembly. We're going to have to write this way so that we continue, so that the function definition that we write can be called either from C++ or assembly. And it's not that hard. So, cleaning up the parameters, again, I know we already talked about this, but let me just refresh your memory. If the procedure that has been called has to clean up, then, and we had 2 parameters, then I return n, where n is the number of bytes that were pushed on the stack. If, as is the case with the calling convention we're using, if the caller is cleaning up the parameters, then what it's going to do after the call instruction is add 8 bytes to the stack pointer. Okay? Alright, so what we're going to do next is we're going to look at an example. The example we're going to look at is factorial. So, that's it, guys. I'll see you in class.